So, in the last class we were winding up looking at the frequency response of the two-stage operational amplifier, and this is the small signal equivalent. So, this is the first stage. GMVI goes into a resistance R1, which is denotes the total output resistance of the first stage. Then there is a parasitic capacitance C1. This is the dominant pole compensating capacitor. This is the transconductance of the second stage. I call that Vx. This is Gm2 times Vx. This is R2. C2, and there is a voltage controlled voltage source, which we said has got such a large bandwidth that for all practical purposes it can be considered a unity gain buffer. Now, after compensation we saw a couple of things. So, this VO of S by VI of S is the DC gain ADC times 1 minus S over omega Z divided by 1 plus S over omega D times 1 plus S over omega naught. This is the omega naught is the second pole, omega Z is Gm2 over Cc, omega D is 1 by R1 times Cc times Gm2 R2 approximately, of course, and the unity gain frequency which is omega sub u is basically ADC times omega D, which is the surprisingly simple expression Gm1 over C. All right, and yesterday we saw the intuition for this result. When we wound up yesterday, we were basically looking at the poles positions of the uncompensated system, right. Remember that the two poles of the uncompensated system are close to each other, right, and so let us call them P1 and P2, and after compensation that Miller capacitor is added, one pole moves very close to the origin, the other one moves farther away. So, this is basically you can see that the poles are split. So, Miller compensation is also called often called pole splitting compensation. And another minor point that I would like to make is that if a company is selling you a general purpose op amp, right, where when you say a general purpose op amp, it means that you have no real idea what the user is going to use the op amp for, right. So, you just assume some broad set of boundary conditions in the sense that you hope that the user will not put a feedback factor with a gain greater than 1, right, and then basically make sure that your compensating capacitor Cc is chosen so that the amplifier is unity gain stable, correct. So, this way you don't have to, as a user is as far as the user is concerned, you don't have to worry about will my closed loop be stable and so on, right. As long as the feedback factor is less than 1, the system will be stable. That is one aspect. The other aspect that I would like to draw your attention to is this whole splitting business, right. So, I mean have you seen something similar occur elsewhere? Okay, all of you probably still remember that you have atoms and then there is electrons going around the atoms, and therefore, there are only discrete levels of energy that these electrons can have, right. So, you have discrete levels of energy, right. So, now when you bring two atoms close together, what happens? And they interact with each other, what happens to the energy levels possible now? Energy levels split, right. If you bring more and more atoms together, the split becomes a band, right. Okay, and what is when you bring atoms close together, right, when you say they are interacting, what does it actually mean mathematically? There is some coupling between two systems basically, correct, and energy levels are related to the eigenvalues of the Schrodinger equation, correct, okay. And so now can you see the analogy here? What are the poles? The poles are nothing but the roots of the characteristic equation, correct, okay. Analogous to the natural frequencies that you have with E equal to h nu type energy calculations, right. And so, when Cc is 0, correct, in other words you have two linear systems which are not coupled to each other, they are not interacting with each other, because the output of the first system is taken to the second system, the second system does not care what is happening to the first one, it just takes whatever it comes to it and then amplifies, right. So, it has two poles P1 and P2, correct. What is Cc doing? It is introducing coupling between these two systems, and therefore, right, what it is only natural to see that just like how energy levels split, they are eigenvalues of a differential equation. Likewise, the poles are basically eigenvalues of this system, correct, okay. And when two systems couple to each other, the eigenvalues will split, right, and that is basically what you are seeing here. If the coupling is weak, then the split will be small, right. If the coupling is strong, you basically will see a large split in the poles, okay, all right. And that is one aspect that I just wanted to draw your attention to. The next thing I would like to address is this fellow here. So, 1 minus s by omega z is a right half plane 0, and that is coming because of feed forward due to this the feed forward path due to Cc. And now we have learnt enough about stability to understand that this right half plane 0 is it's a problem for stability, because it actually even though it is a 0, because the right half S plane, it causes phase lag, right. And I mean another way of looking at it is the following. So, let us say, I mean there are a whole bunch of poles. So, let us say you have a system with say a single pole. So, some A d c over some 1 plus s by omega d, just for argument's sake, right. So, if you put a small step here, what kind of signal will you get here? Of course, you will get an amplified step due to ADC, but what you will it will be, because of the single pole, it will basically do that, correct. Okay. Now, if I add a right half plane 0, how will this look? In the time domain, what is this in the time domain? Let's call this h of t, right. So, this has got two components, one which is, I will write this 1 minus s by omega z as 1, and s over omega z, and there is subtraction here, correct. Yes, okay. Now, can somebody tell me what the waveform here is going to be? This is going to be h of t, What about this guy here? It is 1 over omega z times dh h prime of t. Okay. So, how will this waveform look? How will this waveform look like? How will the derivative of this waveform? This is h of t. How will 1 over omega z, some constant times its derivative? How will the derivative look like? It will just do this, correct, with some constant which is basically some 1 over omega z, correct. Okay. So, now if I so this is some 1 over omega z times h prime of t. So, if I subtract the two, what will happen? So, first we will go negative, then right. So, that is basically the waveform that you see here. Okay. So, now look at the blue curve and h of t and the input and output due to 0. What comment can we make about the blue curve with respect to the black one? It is simply delayed. Does that make sense? Right. Okay. What if I had, instead of subtracting, if I had added? So, if I added a 0 in the RHP 0, how will the output look like? It basically does this. Okay. And LHP 0, what will you expect to see? You get something like this, and then you will get that. And without any 0, okay, all right. So, I mean, so there's basically, you can see there's a time domain intuitive way of seeing why the right half plane 0 causes more delay in the system. A left half plane 0 reduces, another way of thinking about it is, so LHP 0 is h of t plus some k h prime of t, correct. And remember, what is h of t? If you want to advance a waveform, what by a time td, what is the expression? H of t is a waveform. I want to advance it by td. What is the, an advanced version is h of t plus td, right. For small td, this is if you expand it in Taylor series, what does this look like? H of t plus td times h prime of t, and so on, right. So, what is this h prime of t? How do you get h prime of t? This is basically, this is nothing but h of s plus some td times s times h of s. So, this is basically saying that you have a 0 and it is in the left half plane, right. So, this is equivalent to that 0 is attempting to advance the signal, right. On the other hand, if you do h of t minus td, what do you see? This becomes negative, and so this is the, so if you have subtract the derivative, then it becomes delayed by s times td, and I mean delayed by td, and this is equivalent to a right half plane. So, the bottom line is, of course, it also all comes out to the math, but the important thing, the time domain, I mean, I always find time domain intuition, very useful, and so it's always good to be able to look at something from multiple perspectives, and so basically this is telling you that the right half plane 0, because the Miller capacitor is actually degrading the phase margin of the system. Okay. And therefore, since it degrades phase margin, it we'd like to be able to sit and fix this problem, correct, and that is what we are going to see next. So, again let me remind you of the origin of the whole problem. So, this is GM1 times Vi, I am going to throw out all the non-essential stuff and focus on the core root cause of the problem. This is CC, all right. So, ideally what do we want? I mean, let us assume that this right to first order, basically we ideally we want this GM1 times Vi flows, this current flows through CC, causing a voltage drop GM1 by SCC times Vi. Okay. But what is the problem? The actual output voltages, I am trying to understand the origin of the 0, correct. So, what is the output voltage VO? What is the gate voltage? What is the impedance looking in here? One by which GM? So, this is GM2 times Vx. Okay. So, so this voltage therefore is, what is Vx therefore? The looking in impedance is 1 over GM2. So, what is the voltage Vx? Minus GM1 by GM2 times Vi. So, what is the output voltage? That is basically the voltage across the capacitor. Across CC minus GM1 Vi over GM. Correct? So, this is basically GM1 over SCC times 1 over SCC over GM2 times V. Does it make sense? I mean, basically this is saying that at high frequencies that CC is a short. So, whatever is there at Vx will show up at Vo. Okay. So, what is it of these terms which which is the one, so this is Vx. So, which is the term we want and which is the term we do not want? Which of those terms is responsible for the 0? Vx, correct. So, this is what we want, this term we do not want, correct. So, you have the output which consists of two quantities, one which you want and one which you do not want. So, if you want to get rid of something that you do not want, the two fundamental ways of doing it, what are they? You either divide by a large number or subtract, right. Okay. I mean, multiply by a small number is the same as divide by a large number. Okay. So, divide, I mean, so if you want to divide by a large number, what will you do? You want to make GM to infinity, correct. So, one way of getting rid of the 0 is to say I am going to make GM to infinity. Mathematically that sounds great, but in practice what problems will we have? Yeah, the transistor is going to become large, lot of power, etc., etc. So, that is not a particularly smart way of doing it, right. The other way that we can try is to basically subtract Vx. Okay. So, in principle therefore, so if what we need to do is to subtract Vx is, I mean, if somehow we had a voltage source Vx, we could simply add it in series with Vo, and that will give you Vo minus Vx, and therefore we can get rid of the 0. Is this clear? Now, all of you I am sure are aware of, you can always take a voltage source and push it through a node, correct. So, this is equivalent therefore to Vx so what is this voltage going to be? What is that voltage going to be? So this is Vx. So what is this voltage going to be? V naught minus, this is V naught minus Vx. All I have done is pushed this voltage source through the node. Is this clear? Now let us take a look at this voltage source. This is in series with a, what is the transistor? And what is this actually? This is nothing but a current source which is GM2 times Vx. So if you have a voltage source in series with a current source, what is the effect of the voltage source? What does the voltage source do? Nothing. So do we need that voltage source Vx in series with GM2 in the drain of the transistor? So this Vx doesn't, I mean, it doesn't affect anything. So it's not going to change the current. So basically, because it's in series with a current source, so we can remove. Okay. Now look at, let's concentrate on this voltage source. What is the current flowing through this voltage source? What is Vx, by the way? So Vx is nothing but minus GM1. I think we are okay. GM1 over GM2 times Vi. Okay. And the current flowing in that direction is GM1 Vi in that direction. So here is a voltage source, a current GM1 Vi is flowing through it. The voltage developed across that voltage source is GM1 Vi over GM2. So what can you replace that voltage source by? A resistor of value 1 by GM2. Is this clear, people? Right. So this is basically 1 over. Okay. I mean, this gives you, this is a negative voltage, right? This is the same Vx in the opposite direction, right? So the output voltage is basically Vx plus 1 over Sc, plus the voltage across the capacitor minus Vx. So the effect of Vx is cancelled, and therefore you basically end up with GM1 by SCC times. So whenever whenever you are trying to cancel two things, right, what must you be aware of? What can go wrong? You are trying to subtract A with B. Of course, what he points out is you must make sure that you don't add, right? Well, I am assuming that we don't do something like that. Okay, that is a pathological problem. But even if you do it correctly, if you subtract, right, what you subtract will not be exactly what you want to subtract, and consequently there will be some effect, residual effect. So in other words, the 0 will not be perfectly cancelled, but it will become so far away that it becomes, if that omega z tends to infinity, or even goes up by a factor of say 100, because there is 1% mismatch between this GM2 and that 1 over GM2, we are still much better off than we were without the zero cancelling resistor, correct.